Hello everyone. Welcome to this course of chemical crystallography by Professor Umshovan Roy Chaudhary from Ansar Mohali. So, this course has started on 25th July and it will continue for 12 weeks up to 14th October. And I'm the TA of this course, and so every Saturday we have this live session from 3 to 4 pm where we discuss about some topics and assignments. So, this is the Google Meet link where you can join for the live session. And in the as you already must be familiar with, in the SWAYAM portal, in this tab, so you have a tab called Ask a Question. So here you can post your questions, or in the form of, it is like a Gmail platform where you can post whatever doubts or questions you have at any point during the lectures, during the video lectures. And when myself or the professor sees it, we will reply to you. And also when we reply to you, then it will also be possible that the others will also see the reply, so that the others who may also have that question may have that question in their mind, they will also be able to see the answer. So please ask questions here. And so let us move on. Let us move on. So welcome to the 6th week, or the 6th session of this course. The session 6 is being held on the 3rd of September 2022, and today we will be discussing mainly the assignment 4, and related to the questions in assignment 4, whatever was taught in that week. So as you know, so in the week 4 we have been taught about Miller indices and some advanced things about Miller indices, and also planar densities, etc. So we will be talking about that. So this was the first question. Okay, so the question was that what are the Miller indices for this plane? Now, as you know, so we can simply get the Miller indices in the following way. So at first what we had to do is we find out the intercepts from what is given. So the first job is to find out the intercepts on let me turn on my laser. So the first thing is to find out the intercepts on the respective x, y and z axis, and then we have to take the reciprocal of them, and then we have to clear the fractions if only. So this is the simple way to find out the Miller indices. Now how do we find out the intercepts for x, y and z axis? We find out the intercepts with respect to some origin. So here we can see, so this O is the origin, right? And this is my plus x direction, this is my plus y direction, and upwards is my plus z direction. So in order to find out the intercepts for this plane, which is shadowed here as blue, so first we what we are seeing is that there is no way in which it is visibly clear as to where this plane is intercepting by x, y and z axis, because this is kind of like on the opposite side of this origin. So for cases like this, it is not impossible to find out the Miller indices. So what we simply have to what we simply have to do is we have to shift the origin. So this shifting of origin is the solution. So basically we have to okay. So there are 4 options are given here. So we have to at first solve the question to find out which of the 4 answers are true. So if we try to see this, so I have to make it not full screen to write or something, do something here. So at first we see that the origin is here. So at the onset what I will do is I will take the origin here at this point, and I will mark it O. So now this has become my new origin. Now one thing is to be remembered, that although I have changed the origin, still my direction of the x, y and z axis will not change. So from here, this direction is again my plus x, so this opposite direction will be my minus x. Similarly, so if this is my plus y from 0 to y, this is my plus y, then this direction will be minus y. That is, from here this direction will be my minus y. So let me just, so we have this direction which will be minus y, and then this direction which will be my minus z, and similarly this direction will be minus x, right? So now after shifting the origin, we will proceed as to how we normally find out Miller indices for any plane, right? So what is the first option? So my first option is to find out the intercepts. So at what will I do? At first I will find out the intercept along x-axis. So this was my initial x-axis. So what is my x-axis now? This. So this will be my minus x. So this is the half intercept of this plane. Now from origin towards this direction will be negative. So my intercept along x-axis becomes minus half. Okay. Similarly, now intercept along y-axis, so you might be able to say it yourself. So this was my y direction, so this is my minus y direction. So when here this was 1/3, the intercept here, so what will be the intercept now? So now this intercept from here, from this origin, will be 2/3 with a negative sign. The z direction. So what is the intercept along z axis? This was my plus z, so this direction is my minus z. This is right, let me write it, minus x. So this is my minus z. So again, if this is 3/4, then along this we have to reverse the sign as well as subtract it from 1. So if we can do it mentally, like 1 minus 3/4 will be like what? Minus 1/4, right? So I hope it is clear to you what we are trying to do. So after taking the intercept, so now we have the intercept, so let us write it. Minus 1/2 minus 2/3 1/2. Okay, so we have taken the intercepts. Now next step is to take the reciprocal. So reciprocal of this, minus 2 minus 3/2 minus 4. Then the last and final step is to clear the fractions. Now how can we clear the fraction? We simply have to multiply with 2. So if we multiply with 2, this will become minus 4, this will remain minus 3, this will become minus 8. In other words, 4 bar, 3 bar and 8 bar. And since this is the Miller indices for a plane, we will have first brackets. So this is how you can find out the Miller indices for a plane like this. Okay. So I hope you understood. So since we had the origin from here, now since we are shifting the origin, that is why we have to subtract these intercepts. So if we go back to our options, we had 649, 6 bar, 4 bar, 9 bar, 9 bar, 4 bar, 6 bar, and 4 bar, 3 bar, 8 bar. So what we got here is this 4 bar, 3 bar, and 8 bar. Hence, this option A is our correct option. So this option you had to choose in your assignment. This one. So now what we will do, we will move to the next question. So after we discussed about finding a Miller indices for a plane after shifting of origin. So now we come to a different concept. This was probably taught in your second class of week 4. That is something called as the planar density. Now, so there was a question from one of you that what exactly do we mean by planar density, and the basic explanation of planar density. So if we talk about planar density, so this is a very simple idea. So it is just like the amount or the volume of volume occupied by the constituent particles in an area. It is nothing that. So suppose when we talk about three-dimensional systems, so we have learnt about the cubic systems. We have learnt that we at first about the primitive cube. So where only the corners, the 8 corners are occupied by some atoms, right? So in the middle there is some void. So if we find out the volume of the cube, so suppose if the length of the cube is A, the volume of the cube will be A cube. However, the entire volume, that is A cube, is not occupied by the atoms, right? So there is some void. So the ratio of the volume occupied by atoms to the volume of the entire cell is the packing fraction in case of the 3D cube. Now if we talk instead of the cube, if we talk about a plane, then what we get after dividing the volume occupied by the atoms divided by the not the, here we will not talk about the volume, we will talk about the area. So the area covered by the atoms divided by the area of that plane is what will give rise to the planar density. So since it is a plane, this is simply the two-dimensional version of the atomic packing factor. So this can so the planar density can also be called as the two-dimensional packing factor. So here let us understand this by an example. So suppose we have 8 atoms and all of them are equal. So we will assume that the radius of all the atoms are equal, and hence correspondingly the volume of all the atoms will also be equal. So if we have 8 atoms here, then suppose we chalk out our area like this, okay, like a box like this, and we want to find out what is the planar density of this area. So this can be regarded as a plane, right? So if we consider this as a plane, we can see there are some voids here. So all of the area of this plane is not occupied by some atoms. Hence we can say that we can find out the ratio of how much area is occupied by this atom. So this is nothing but the planar density. Now let us proceed to do that. So how can we do that? At first what we have to do, let us take one R, which will define the radius of these atoms. And since I have said before, so we are assuming that all these atoms are identical, which means the radius and the volume of all these atoms will be the same. Hence if we take this R, so if this is my R, then this much is also R, right? So if this is R, then this much area is also R, right? So at first let us find out what will be the area of this plane. So we have one R here and here. So normally for a rectangle, what is the area? This is L, that is the length. This is P, that is the breadth. Then area capital A is equal to L into B, that is length into breadth, right? So here also the same thing, we have to find out this length, and then simply multiply. Now this length is easy, right? So what is this? This is R plus R. This is my 2R. What is this? If this is R, then this is the becomes the diameter. So this is 2R. So we have 1R here. We have 2R here. Then again 2R here, and here another R. So 2 plus 2, 4, 5, 6. So we have 6R. So this, obviously this is equal to this. So this area is my 6R. And what is the area of the plane? 6 into 2, 12R square. So 2R into 6R, which is 12R square. Now we have to find out the amount of area which is occupied by the atoms. So how to do that? What is the area of a circle? This is a circle. Since we are talking about a plane, we are talking about the two-dimensional packing factor. So here everything is in 2D. Hence we will not talk about the volume. We will talk about the area. So area for a sphere is equal to pi r square, right? So here if we talk only about this much, then how much area is this much? This is 1/4 of it, right? Because if this, we draw a line like this, this is half, this is half. So if this is half, then half of this much. So mark it. So this much is 1/4. So how many 1/4s are there? We have 1/4, we have 2/4, we have 3/4, this is 3, okay, and we have 4. So 4 into 1/4 pi r square. So we got this term. Now what about these? These are halves of pi r square. So half of pi r square, how many are there? 1, 2, 3, pardon my 3's, and 4. So 4 into half pi r square. So now we also got this term. So now if we total it, so this is simply pi r square, right? 4 and 4 will cancel out. This is simply pi r square. This is 2 pi r square. So pi r square plus 2 pi r square gives us 3 pi r square. And area of the box we have already determined previously. This is 12 pi r square. So if we just divide it, we will get 3 pi by 12 or pi by 4, which comes out to be this percentage if we multiply by 100. So 78.54% of this box is occupied by circles. This is nothing but my two-dimensional packing factor of this plane, or the planar density. Now if we think of the 2D plane, we can understand that the atoms can be arranged in this way, or it can also be arranged in this way, right? So there can be a question as to which is like the better packing. So for that we have to find out the planar densities for both the cases. We have to find out planar density for both the cases, and then compare which is more. So one which is more will have less void and hence better packing. So that is what they did in this example here. So they now arranged the atoms like this. So here also we have the same concept that the atoms are equal. Okay, so here how will they derive the relation? So they are deriving the relation like this. So this is also very easy. So we first have this length and then we have this length. However, here it is not, we cannot basically determine the length like this, because here they were all connected, so we could just simply add it up. But here we cannot add it up in this fashion, so we have to join like them. So what will we do if we join like them? What is the length here? So the length here is given already. So this is r, this is 2r, this is r. So this much is my 4r. Okay. So if this much is my 4r, then what are they doing? So they are basically making I'm sorry. So they are basically making a triangle out here. So if if this is a right angle triangle, then we can get this area, this length also and this length also, and then followed the similar procedure is followed here as to what was followed here. Okay, and then we find out the area of the circles in the box from here, and also the area of this box. And then similarly we find out the atomic packing fraction, which also comes out to be the same percentage as before. So from here we can understand that even though the atoms are arranged in two different manners, still both of them have the equal planar density and hence equal packing in two cases. So this is all about planar density. So now we have this question, right? So what is the planar density of the 111 plane of BCC unit cell? So we will do this question, but before that we will just look at the diagram once to understand one very important point. What is that point? If we have a body-centered cubic cell, so these are the corner atoms. 1, 2, I'm not naming them, there are 8, 1, 2, 3, 4, 5, 6, 7 and 8. This is the central atom. The crucial point is the 111 plane. So this is my origin. The 111 plane means it will cut my x-axis at 1 unit cell length, y-axis at 1 unit cell length and z-axis at 1 unit cell. So the triangle formed in this manner here does not actually contain this atom, because in the body centered cubic cell, so we have an atom at the center, right? So with coordinates, it is half half half. However, this atom does not belong to this plane. Hence, while calculating the planar density for this plane, we will not consider anything about this atom. And what will we consider? We will simply consider a triangle with some fraction of the sphere here. So this is 1, this is 1, this is 1. And now again, although in the body-centered unit cell, the atoms are constituted as spheres. However, we are talking about the planar density. We are talking about a plane, and hence we will talk about area. So upon simplification, we get to this point where we have a triangle. Since this is a cubic lattice, so since this is a cubic lattice, so the lengths of the triangle are same. So this is what is called as an equilateral triangle. So we have an equilateral triangle here and some portion of the circle here. So what is the portion of the circle? This, if we can just extend the parts of the circle and find out that this is actually 1/6 of a circle. So if we consider pure geometric relations, draw a line like this, stand like this. If we divide it, so this one part will be my 1/6. Okay. So you get the idea. So now we will calculate the amount of the area which is occupied by the atoms in this triangle basically, and also what we need is the area of this triangle. Now we have a formula that if for an equilateral triangle, so if we have an equilateral triangle with length A, equilateral triangle means all the three lengths are equal. So what is the area? Area is root 3 by 4 into A. Okay, so we will need this. Okay, so this is the area. Okay, and then 1/6 of the area of the circle. So what is the area of the circle? The area of the circle is pi r square. So now if we go to the calculation, okay, so from here we will have three atoms with 1/6 pi r square. This is 1 pi square. Divided by root 3 by 4. What did I write? I hope you remember. So root 3 by 4A, where A is what? A is my, one second, yeah, so A is my this thing, area of length of the edge. Okay, the A is the length of the edge of an equilateral triangle. So what we need is, so we need the area of the plane. So how will we find out the area of the plane? If we consider this plane, yeah, just pardon this part. If we consider this plane, then this is what? This is simply a face diagonal, right? So this is simply a face diagonal with with length equal to root 2 into A, right? So for this triangle, so this is my root 2 into A, this is my root 2 into A, this is my root 2 into A. So root 2A is my length. So here, to avoid the confusion, I should make it L. Okay, where L represents the length. So this is root 3 by 4 into L. Because L is my length, edge length of the triangle. So root 3 by 4 into, so root 3 by 4 into my root 3 by 4 into square of the edge length of the triangle, which is my root 2A. Root 2A square. So I hope you do not have any confusion. because so let me just put this slide here. Okay, so what we have, we need the volume of the we need the area of the atoms. So we have 3 atoms, and for each atom we have 1/6 contribution, so it's 3 into 1 by 6. Now we need the volume, again we need the area of this plane. Now area of this plane will mean area of this equilateral triangle, and area of an equilateral triangle is root 3 by 4 times the edge length. And what is the edge length? The edge length is equal to root 2a, because this is a face diagonal. Okay, so here you got it. So if r is the radius of the circle and a is the for this BCC lattice, the unit cell length is a. So for a BCC lattice, what is the relation between this r and a? Because to get a fraction, so here we have r, which is the radius of the atoms. Here we have a, which is the unit cell length of the BCC, edge length of the BCC unit cell. So in order to get the fraction, we have to bring both of them into some common ground, right? So what is the relation for BCC? So when we have a body diagonal, so what we have is, so for a body diagonal, 4r is equal to root 3 times a. What is my body? Because this is very easy actually. So you just draw a BCC lattice. So here we have one, assuming full packing. We connect them. So we have root 3 equal to 4. Now you just simply have to substitute and you will find out the value. So we can do that. So this will just simply become my half pi r square, right? So because 3 by 2, so pi r square. So this 2 will come here into root 3 by 4 into this root 2 square will become my 2. Yeah, so I'm not doing it because you just have to substitute this here, this r square, you just simply square it. So this is 16 r square is equal to 3a square. So we have 2, then a square, then a square means 16, don't have space. Yeah. So we have this. So from here we are going. Okay. So at first we'll draw the line. 3 pi r square by 6 into root 3. This 4 will go up. Root 3 a square 16 r square by 3. R square will cancel. 4 is 16, 3 2 is 6, So you will get, so just you can do it, because I do not have calculator here, so you can just proceed in this way and you will get the value. Okay, so we discussed about the planar density part. So then we had this very easy question: what is the coordination number for BCC lattice? So I hope all of you have answered this, because it is like very simple. We just have to so if we just consider here, so how many atoms is it linked to? So we have one here, one here, one here, one here, one at the back, one at the front, the back. So we have 1, 2, 3, 4, 5, 6, 7, 8. This simply the answer is 8. So I hope all of you have answered this. Then we have this question: what is the atomic? I'm sorry. What is the atomic packing fraction for BCC lattice? So atomic packing fraction means it is in 3-dimensional. It is basically the 3D version of this planar density, right? So in order to find out the atomic packing factor for a crystal system, we have to take the volume. Take the volume which is occupied by the atoms divided by the total volume of the unit cell, which will give me my atomic packing factor for any crystal system. Then if we, of course we have a initial assumption, that is all the atoms will have the same size and are arranged in a repeating crystal lattice. So if we assume that all the atoms have the same size, then we can go a step further and then equate the volume taken by atoms as the number of the atoms multiplied by the volume taken by each atom and divided by the volume of the unit cell. So here V represents respective volumes. V with the subscript atom means volume of one atom. V with the subscript unit cell means volume of that unit cell. N means the number, and APF is the atomic packing factor. So so from here we can find out the atomic packing fraction for the BCC lattice. So here also it is again the same thing basically. Sorry. So we have the body diagonal starting from here to here, which is my root 3a, which is combining one atom here at the center like this, one atom here, one atom here. So this will be my 4r, where what is r? R is the radius. So for one atom I have my radius as r, and this is my A. So we have the body diagonal starting from here up to here. This root 3a is equal to 4r. Then simply what we will do, we will find out what is the volume of the unit cell. Volume of the unit cell is my 2q. And what is the volume occupied by the atoms? So we have first 8 like before, so just like the before slide. So we have 8 atoms at the corners. So, and how much is each atom contributing? So we know, right, that each atom contributes like 1/8. So we have 1/8 into 8 of pi r square. So that simply gives rise to pi r square, because we have 8 atoms contributing 1/8, plus the central atom is contributing the whole to the unit cell, right? So this gives rise to 2 pi r square. So what is the what is my atomic packing factor? This is 2 pi r square divided by a cube with this relation. So a means 4r by root 3. If a means 4r by root 3, then we can cube it. So we have 2 pi r square Oh, I am so sorry, I made a mistake. So pi r square is the area for the volume. So volume is a cube and V atom is 4 by 3 pi r cube, right? So volume is 4 by 3 pi r cube for a sphere. So we have 1/8 of that. By 3 pi r cube, because the volume of the central atom is a whole of 4 by 3 pi r cube. So this what would, if you combine it, so this is just 2 times 4 by 3 pi r cube. So atomic packing factor will be the ratio of the volume occupied by the constituent atoms. So this is 2 multiplied by we have 2 multiplied by 4 by 3 r cube divided by a cube, which is my this 4 for the 16, 16 for the 64 r cube. Well, what is the cube of root 3? So this will be 3 root 3. Now at first r cube will go. This 3 and this 3 will go, right? Then we have 4 2s are 8. Then we have 64 at the bottom, and this root 3 will go up. So root 3 by 8 pi. If you do this, it will come out to be 0.68 or 68%. So you can just use a calculator for that. Okay. So then we proceed to the next question. So the question was that in Bragg's law, the theta is simply the angle between normal to the parallel lattice planes d distance apart and the incident ray. So this was a true and false question. So first we will simply draw some planes, and we will constitute the Bragg reflection. So we could also have done it for this plane. So let me do it for the first plane, then it will be easier to understand. And this point is the normal to the plane. This is theta. The question, what is theta? Theta is the angle between the incident rays and the TH and the HKL planes. But the question was the angle between normal to the parallel lattice planes. But theta is actually the angle between the parallel lattice planes and the incident rays, which is theta. Hence, this is false. Then we had another very interesting question. So we had this 100 direction and 001 direction are opposite to each other, which is again false, because if we have a direction which is my 100, then this opposite direction will be minus 100, right? We have learned about finding the Miller indices of the directions, right? So this point is my 000. Then this is my x-axis, this is my y-axis, this is my z-axis. So this point is my 100. This point is my 000. So this direction will be 10. So we have to subtract the base from the tip. Then if we want to find out the opposite direction, right? So then this will become my tip, this will become my base. So what we have to do, if this is becoming my tip, then the 000 will go, and here we will have 100. 0 minus 1, which is equivalent to 1/0. Thus this is false. Okay, so then we had this. So then we had another question. So this is also a very easy question, that whether half of half is a lattice point in the BCC unit cell or not. So we will again draw body centered cubic lattice. So we have lattice points. Actually, it is becomes very bad to draw the lattice points with pen. So let me draw with this. Here. this actually is my origin. This is my origin. This is X, this is Y, this is Z. So this is origin, this is 0, 0, 0, and then it's 1, 0, 0. What will be this? What will be the 1, 1, 1 point? So 1, 1, 1 means 1 along X, then 1 along Y, sorry, 1 along X, then 1 along Y, 1 along Z. So this is like 1, 1, 1. Okay, so this is and then if it is a body centered unit cell, we will have another point at exactly the center of the unit cell. So this is the point under consideration. So to find out the atomic coordinates for these points, what we will do, we will start from the origin. Okay, so we have to remember this is at the center, right? This is not on this face, this is at the center of the cell. You have to imagine the cell in 3 dimensions. So to reach here, so what does it look like? So at first, if we just move along Y half, move along Z half, then the point which we will reach will be actually in this plane. Okay, so it will be in this plane, so which is not this point. It may look so from the image, because we are trying to project a 3-dimensional cube in 2D plane of the, in the 2D screen of the computer. But if we just go along Y and Z, we will reach somewhere on this face, which will be, what will be the means that is a coordinate for what? That is the coordinate if we were talking about a face-centered unit cell, right? But this is a body-centered unit cell. So what is the difference? So this was my, rather, this is my BCC, this is FCC. Let us draw all the points for FCC first. The origin, now we will draw the atoms at the centers of the faces. For this face, it is this face, it is here. For this down face, it is here. Now what about this front face? For this front face constituted by this, it will be somewhere here. For this face, it will be somewhere here. Now we have for this back face, somewhere here, which is the center of this plane. But here all the atoms are on the faces and none is in the middle. But here, if we want to find out what is in the middle, so for the middle atom, we have to go half along X also, means in the front, because the origin is kind of at the back. So we have to move half a unit cell along the front, so we have to come here. So then what will be my trajectory? So my trajectory will be half here along x, half along the y direction, then half in the z direction. Then I will reach the center of this unit cell in space. So that is the difference between this body-centered lattice and the face-centered lattice. So here we do not have any unit cell named half of half. All of these are on the faces, or the corners or at the centers of the faces, right? So sorry. Okay, so that's all. So then today what did we discuss? So we discussed about mainly the questions given in the assignment 4 of week 4. So the due date was on 24th August. So I presume so all of you have already submitted the assignment. So I have discussed it today. So then at first we talked about the Miller indices. So I hope you do not have any confusion, because so there can be a confusion where, when we are deriving Miller indices for a plane with given intercepts, like here. So here the intercepts were given and we were deriving the Miller indices, but there can also be a question. So this question was there in the previous assignment, where the Miller indices were given and you have to find out the intercept. So this is the reverse process, where when the Miller indices are given, you have to go back and work out the respective intercepts on the x, y and z axis. So these two are different. Okay, so many of you so have this confusion. So both of them will not follow the exact procedure, right? So you have to understand, when the question is given, you have to understand very nicely. When you have to find out Miller indices for a given plane with given intercept, and when you have to find out the intercepts on the xyz axis provided Miller indices, that is the HKL values are given. So sometimes HKL values may be given and you have to find out the intercept. So this question was about finding the HKL for this plane. So we solved that. We also solved this planar density and this detailed calculation. So I leave to you. If you are not able to match it with the given option here, so you can hopefully understand that the options in bold are the given options. So even after working out, you feel that the answer is not matching, then please post this. So with a screenshot or something, you can post this in the ask a question tab, then I will look into it. But I feel that if you work this out, so you will get the expected answer. Okay. Then we talked about the details of the planar density and also the atomic packing fraction. So I guess yeah, so then that's all. So thank you for attending this session 6 of the week 6, and so thank you for your attention. So then I will be closing it. So meet you next week. Okay, so thank you again.